Next talk in this session is on calorimeter given by Professor Sunanda Banerjee. And actually, I'll take few minutes about to introduce him. This is not the official, some personal tasks also there. So he started his career in Imperial College on kaon physics. That time this charm was not discovered yet. So from the kaon to exotic search, that is starting point. Then he went to the cello experiment at Petra. Then he come to the L3 experiment. And in between very short times, he was in Bell. And last almost 20 years or more than, actually in between, not 20, it is more than 30 years since CMS experiment. So this is the span of the things. But his work physics-wise, he was the mainly QCD physicist. And there's an evolution of alpha is that plot, I think in this year, many times you have seen. And from 20 to 200 GeV, the data point, most of the data point either he made or his student made. And also similarly, this electric physics, the jet boson mass and resolutions, width resolutions, we know the 2 MeV resolutions. And there also he has a huge significant contributions. So that's the physics, but here's some other thing also I have to tell you. So he was the main person, one of the main person to make this L3 calorimeters and also the CMS outer hadron calorimeters. This is he made it. But his main strength in this experiment is the softwares. And he was one of the main person from the L3. That time it called the simulation of L3, SI-L3, and reconstruction of L3, it is called the REL3. Officially, he was not in charge, but in L3 people used to know him either as SIL3 or REL3. So that was the nickname at L3 time. Similarly, for the CMS, starting from this detector, starting from the design, this tracker design, he started the design of the tracker. What will be this our silicon trackers? And also same way, the design of this hadron and lead tungsten crystal. What is the crystal? Okay, choice of this crystal. What is the crystal size? That's also came from his simulation or his guidance on the simulations. So that part, and also this detector-wise, many of you did this scintillator experiment in plastic scintillators, and some of you told that it was made 27 years back. Yeah, I made it, but it is under his guidance. Okay, so this is this experimental side, this is things but here's another figure. He is one of the developer of the GANT4 softwares, GANT3 and then GANT4. So that means most of the people use it. And almost all the experiment trying to get his help for the simulation, particularly the calorimeters. So that's why he will give you the talk on the calorimeters. And last but not the least, he is my mentor. I am here because of him.
Many thanks to Govinda, and I do not know, who can give a better introduction to me, and all the compliments he has given to me. Thank you very much, for all the compliments you have given to me. Anyway, I'll be talking about calorimetry, and obviously, I will not give a very high-profile talk about the calorimetry. I'll start only from the basics and try to talk about what really went into the calorimetry as such. So in my first lecture, this is the outline. I'll just have an introduction. Then I'll talk about the interaction of particles with matter. And the basic thing is that how the showers are formed in a detector and how one try to design a calorimeter. And all the content, of the talk, I extracted, mainly from 3 books. I considered this gentleman, Richard Wigmans, is the living legend of calorimetry. So obviously there are 2 books which is Wigman's book, and there is also some article by Chris Fabian in this book by Tom Farber, which is a collection of experimental techniques in high energy physics and particle physics. These are pretty old books, but I learned from them, and so obviously, I recommend people, to take a look at these books. Now, I do not know what any word of Latin, but I know that calor in Latin means heat. So it is it means, we are really want to measure the quantity of heat which is exchanged, and that is what the calorimetry is meant for. Now, a calorimeter is a device which essentially making such measurements of the heat content, which is there. Now, you must know from quantum mechanics that you can never measure a quantity. Whenever you try to measure a quantity, you essentially destroy the quality of that particular measurement. Now, how much you can destroy? You can destroy totally, or you can destroy partially. And that is the difference between a calorimeter and a tracking device. In a tracking device, you destroy the particle, loses a part of its energy in the form of ionization, and from that you try to measure its trajectory, and from the trajectory you can measure the momentum. But in a calorimeter, essentially you destroy the particle totally, and the total energy is absorbed, and the absorbed energy is converted into some sort of a measurable quantity, which you can call heat, which you may not call heat, but the absorbed energy is somehow measured. Now, calorimetry is something we started long time back, and as a very cheap instrument per se, to do the measurement, but it became quite popular when it started having this collider experiments. In collider experiments, I think the first collider experiment in which I was involved had, it's called a cello detector, and that contained a calorimeter which was trying to measure the energies of photons and electrons. And nobody bothered to measure the energies of hadrons in a calorimeter at that time. They're only measuring electrons and photons, and all the other charged particles were measured in a tracking device. The concept of measuring the energy of hadrons in a calorimeter came much later. In earlier times, I remember one of the first calorimeters which I saw was in a neutrino experiment, which is called WA1, where they try to measure the neutrinos, who can measure the structure function of the neutrino, and they really observed that the structure function really deviates from the scaling violation in a logarithmic way, and that was one of the first quantitative tests of QCD, and this was an experiment which was led by the famous scientist Jack Steinberger. I think sometime back when we're introducing this for the what do you call it? Again, getting forgotten. The WA2 experiment, I remember the WA1 experiment, which was the preceding collaboration, which was led by Jack Steinberger, and we are really doing an experiment in neutrino physics at that time. Now, in modern colliders, calorimeters form a very crucial components measuring the energies of electrons, photons, and as well as jets. I'll come to the reason why we're concentrating on the measurement of hadrons in the calorimeter these days, because I'll come to that next. The interaction of the incident particle with the detector materials through all the processes, the electromagnetic weak or strong process produces a shower of secondary particles, progressively degrading this energy. So what one has to do, you are essentially destroying the particle and generating new particles. So all you have to do is you have to count the number of particles. So the simple thing is that it is essentially a counting experiment. You count the number of secondary particles, and then you can get the energy of the particle. The principle is as simple as that, but obviously, the counting is not very simple, and that's why many of the techniques come in. Now, this whenever you produce a number of particles, you know, okay, I mean, it follows a Poissonian statistics, and a Poissonian statistics means, okay, the uncertainty in the number counting goes as square root of the number of particles produced. So how well you measure the energies has intrinsically a 1 over square root of n, and which is n is proportional to the energy, so it goes as 1 over square root of v. So that is the intrinsic thing which comes in the calorimetric measurement. Now, as I said, okay, I mean, generally a calorimeter is related to the heat energy exchange between two bodies. Now, if you really want to look at how much heat is produced, you are considering a very high energy experiment. That means particles have a very high energy. But if you really look at the individual energy of a particle, the individual energy of a particle is extremely small. So if you have a 100 GeV particle, which is absorbed in a 10 kilogram of iron, it will increase the temperature by only something like 10 to the power minus 12 degrees centigrade, which is impossible to measure. So obviously, we cannot refer to the change in temperature in measuring the energy, you have to rely on some other methods. And this is the thing, okay, which has gone in, okay, I mean, there are many ways of doing things, and I'll come to those things, okay, in a slightly different way, in a later part. The deposit energy in the detector material is eventually converted into some electrical signal, and you essentially measure the electrical signal which has been generated. And the thing is, okay, I mean, one knows that the showers which are initiated by hadrons are distinctly different from the ones initiated by electrons and photons. Though we call hadrons are strongly interacting particles with the high cross-section, but if one really look at the cross-section of electrons being light, has a cross-section at the level of barns, whereas the hadrons have a cross-section at the level of millibarns. So the electrons really get absorbed very, very quickly, and that really gives rise to one type of signals which goes in the electromagnetic calorimeters, whereas the hadrons who come in, though they have cross-section in the level of millibarns, okay, I mean, they need a much larger distance to get totally absorbed, and that gives rise to hadron calorimeters. And the hadron calorimeters are distinctly different than electromagnetic calorimeters, and I come to that, okay, I mean, later on. Now, before going through anything else, okay, I mean, first let us see, okay, how a particle interacts with the material. I think this has been shown by many people, okay, in the past. Okay, the main thing which comes in is that the physical process is basically classified into two categories. One is the discrete process. That means, okay, for example, any charged particle goes through, and when it goes through passes through a nucleus, okay, it has called Bremsstrahlung. Some particles can also, like positrons, okay, can interact with the electrons in atoms and annihilate. Obviously, that go through this elastic scattering. These are all discrete processes. In addition to these discrete processes, you have the continuous processes like energy loss or multiple scattering, though they are not quite continuous, okay, but they happen so often, okay, they are classified as continuous processes. Now, the continuous energy loss is, I think you have looked at this formula. This is the Bethe-Bloch's formula. And in Bethe-Bloch's formula, you have the first thing is that you look at this term over 1 over beta square. And at very small beta, the energy loss decreases with momentum. And that's exactly what we are seeing here. You have you have the energy loss as a function of momentum, and you have got bands for various different particles, pions, kaons, protons, muons, and even electrons. And apart from electrons, in all the other particles, you saw this 1 over beta square drop. Then it reaches a minimum around beta gamma 4, and then the gamma square terms start dominating, and you have this so-called relativistic rise. And finally, you have the effect of the density of the material, and you have the saturation effect. So this is what the things which really are doing that. And the thing is, okay, the individual collisions usually are classified as two types, or even three types. One is a distant collision, where the atoms really act as a whole. This is the process which is called excitation and ionization. Then you have a close collision with the atomic electrons, where you have the electrons are knocked on and you produce so-called delta rays. And then there is very close things, then means, okay, I mean, it's no longer with the atoms, but with the nuclei, and that is the place where we call radiation. Now, if you really look at the cross-section as a function of the energy, at very low energies, okay, obviously, these are all distant collision, and here is the excitation processes of it excites the electrons in the electrons band. Then is the process where you have the ionization, and then it comes to the place of the radiation. Look at things, and you see the cross section really falls, so coming logarithmically, or coming very, very fast. So if no discrete process happens, but particles eventually stops after losing all its energies, and that is called is the range of the particle in this medium. So here, I think I have plotted the range of this particle as a function of energy, and you can see the range momentum table, okay, I mean, is roughly very, very similar in the variety of materials, okay, I mean, particularly in the metals like lead or iron. Now, if you really see the stopping power, Bethe block does not give you the full picture of the stopping power. This is for muons. Bethe block really is operating, okay, in a region, okay, from about 10 MeV to something like about a GeV for the muons. And at a very high energy, at 1000 GeV, 100 GeV, okay, the muon bremsstrahlung comes in, okay, and that's where the radiation loss comes in. And at very low energies, okay, obviously, okay, there is a much more atomic effects comes in, okay, and they are described by either Anderson-Ziegler effect or the Landau-Schaff effect. So I think, okay, I mean, there are the stopping power of a muon. This is a stopping power of muon in copper. Okay, I mean, similarly, okay, you can get it from many other materials. And one should remember, okay, I mean, that not everything is done by the Bethe block, and you have to remember the other processes which takes in. Now, if you look at the discrete processes, what are the discrete processes? We have already talked about bremsstrahlung. Bremsstrahlung is nothing but the charged particle interacting with the nucleus, with the exchange of a virtual photon. And then in this process, it really emits a real photon. Annihilation is a positron reacting with the atomic electron, who come in to give a pair of real photons. You have the elastic scattering, then you have the pair production process. And pair production process is very similar to this bremsstrahlung process. It's just inverted in a slightly different way. The photon comes in, interacts with the virtual photon, and it gives rise to a pair of electrons and positrons. Then there is a Compton scattering. Photoelectric effect is a scattering of the electron with the atomic photon with the atomic electron. And then you have the decays of unstable particles, and then there are strong interactions. Now, the strong interactions are classified into 4 categories. I think either the target breaks down, or it remains the same, or the projectile breaks down or remains the same. If the projectile remains the same, it is elastic scattering, or if the target is unchanged, it is called a coherent scattering. So all these are discrete processes has to be considered, okay, when a calorimetry has to be made into business. Now, the idea of a shower comes in, okay, from the idea, okay, how the cross section behaves as a function of energy. This is the essentially, to some extent, represent the cross-section as a function of energies for electrons or positrons. This is the ionization loss. This is the Bremsstrahlung. Then you have the annihilation, and then you have the the elastic scattering. Okay, I mean the elastic scattering for the positrons is the Haber scattering. Elastic scattering for the electrons is the Euler scattering. So these cross sections are small, and if you really look at energies around above 10 MeV, okay, I mean then you can see the main cross section is Bremsstrahlung. So the Bremsstrahlung is the main process by which an energetic electron really interacts with the matter. For the photon, this is the cross section for photon. Photon has at high energy dominantly goes through the pair production, and when it goes down below 10 MeV, okay, I mean then Compton scattering comes in, and at very low energies, photoelectric effect comes in. So the energy dependence of the cross section is the thing which really determines, okay, how a particle, either electron and photon, will go through matter. So at energies above 100 MeV, okay, I mean E plus E minus loses is mainly through the Bremsstrahlung process, emitting photons. And at similar energies, photons interact mainly through the pair production, generating electrons and positrons. Now, if you really look at high energies, okay, the cross section is more or less constant. So this gives rise to this process. Okay, I mean, for example, if you start with an electron Bremsstrahlungs to generate a photon. Photon gives a pair of electrons and positrons, and that gives rise to again a Bremsstrahlung, and the same thing, okay, I mean, goes on and on. Okay, so you eventually get a cascade, and in every step, okay, the energies of the secondaries is degraded, okay, I mean, in the process, and this process continues till the energies of the particles reaches some critical energy. And at that critical energy, okay, the cross section for either Bremsstrahlung or pair production cannot happen. And obviously the other processes takes over. And that is the place, okay, where the ionization takes over and the shower decays out. And that is how, okay, the electromagnetic shower is formed. Now, when you try to look at the electromagnetic shower, okay, I mean, the thing is that the energy loss due to radiation is governed by something which you call radiation length. And the thing is that the energy loss is proportional to the energies of this particle, and the radiation length is related to the Z of the material is related to the charge of the thing as well as the Z of the nucleus. Now, both Bremsstrahlung and pair production cross section, as I said, are very highly forward peaked. So the lateral growth of the shower comes dominantly from multiple scattering at these energies. Okay, I mean, there is the Bremsstrahlung and pair production does not really makes the shower, okay, grow laterally, okay, and only multiple scattering really gives rise to some sort of a lateral shift. But when you go to the low energies, that means you go to energies at the critical energies, then you really follow the energy loss goes as a critical, it goes as an exponential, the delta ddx goes proportional to EC by LR, and then at these places, okay, the two processes which take over are the Compton scattering and photoelectric effect, and those things are isotropic, unlike, okay, the pair production and things, and that really gives rise to the lateral shower size. And the shower profile is then determined by something which is called a Mollier radius. And this Mollier radius is again related to the properties of the medium. It is related to the radiation length and the critical energy, okay, of the thing. Okay, so it is roughly A by Z, okay, I mean in terms. So with this thing in mind, okay, I mean, you try to take a look at how a shower is formed. This is the energy deposit as a function of depth in I think this is in lead, and there are energies of 1 GeV, 10 GeV, 100 GeV, and a TeV, and you can see, okay, the peak of the energy deposit, okay, I mean, comes in, okay, at a smaller distance for a low energy particle, and it grows, okay, I mean, as a function of energy. Now, the thing is, okay, the 98% of the shower is contained in something which is related to the radiation length of the object, and the thing is, okay, and the Tmax, okay, I mean, which is here, it increases only logarithmically with the incident energy. So if you want to work with a 1 TeV particle, electrons and photons, you only worry about something, okay, which goes as a logarithmic energy of the thing, okay, and that is how it determines the size of the particular detector. If you really want to see this, measure the momentum of the particle with the same type of precision, obviously, okay, the precision, if you require the precision, it goes as the square of the length. And that's why, okay, calorimeter becomes much more important, okay, than a tracking device when it goes in energy. You can measure with this equal precision, okay, I mean, the energy of electrons and photons with a calorimeter than with a tracking device if you really want to make a compact detector. Now, there is some difference between the electrons and photons when this shower starts. Electron, from the very beginning, okay, I mean, it starts depositing its energy, but through this ionization process, even before it has a Bremsstrahlung photon. But while, okay, photon, okay, I mean, cannot deposit its energy till it tries to make a pair production. So that's why if you really look at the energy deposit as a function of distance, in the first 5 radiation length, okay, I mean, you can clearly see, okay, electrons deposit much faster, okay, compared to a photon. So that may be a way, okay, I mean, you can distinguish a electron shower from a photon shower. But if you have a large enough detector, okay, where you try to absorb the total energies of a high energy thing, okay, you cannot distinguish electron shower and photon shower just by the calorimeter itself. Then you have to rely on something which has really come, a tracking device, okay, which is in front, okay, which says, okay, I mean, there's a track which is hitting the, which is a track which has hit the calorimeter in front, and that's the electron. And if there is no track, then it's a photon. Now, when you go to hadrons, okay, it is very similar to electromagnetic shower, but it has got a greater variety and complexity due to the hadronic process. So this is essentially a picture of a emulsion, which I think has been talked about, okay, in by some previous lectures. You have a 30 GeV proton which comes in, okay, and hits in the nucleus of a emulsion, and you have got several types of particles which has come out. Now there are the types of particles which have come out. You can see very faint particles. That means, okay, they are minimum ionizing particles. That means these are high energy particles. Then you have got very deep tracks, and this is nothing but low energy, essentially protons or nucleus. Nucleus, which deposits very high amount of energy and stops inside the thing. So you can have, okay, I mean, various different types of particles which will be produced. And obviously, okay, I mean, whenever there is a particle, okay, I mean, if it is a high energy particle, which is hitting, 90% of the particles which is produced are pions, and 1/3 of those pions are neutral. Now, whenever neutral pions are produced, it will decay to pair of photons. So, and pair of photons will come in, they will give rise to electromagnetic showers, whereas the pions will only, charged pions will only deposit the energies through ionization process. So we have got two different types of energy deposits in the whole process. One is goes to the so-called electromagnetic showers, the other is due to ionization loss. In addition to that, you have got also neutrons which are produced, okay, which carries neutrons and other neutral particles which are produced. Obviously, they would not deposit this energy until it does a secondary interaction and produces further charged particles in this process. But whenever a nucleus is broken up, there is a binding energy of the nucleus which has to be provided. So in that case, okay, I mean, this binding energy is compensated by the energy of the incident particle. So you lose some of these energies in this process. So obviously, okay, I mean, when you have a hadronic shower which is generated, you produce some particles which is proportional to the energy of the particle, but you are at the same time, because of the nuclear effect, okay, I mean, you lose some of the energy itself. And then you have the competition between EM showers and hadron showers. Typically, the electromagnetic energy fraction, again, okay, I mean, is different. Okay, is a function of momentum. 30%, it is 30% at 10 GeV, and it is 50% at 100 GeV. So I mean, these are the things which really complicates, okay, the hadron showers development. Now, the thing is, okay, I mean, the ratios of the energies, okay, I mean, which is divided among the various ionizing particles, neutrons, and invisible components is something like 56 to 10 to 35. And 2/3 of the ionizing energy is due to protons. Okay, so I think all these complications, okay, I mean, really makes a hadron calorimeter or hadronic showers, okay, I mean, quite difficult to handle. On top of that, okay, I mean, you have got various other properties, okay, which is happening, okay, I mean, where exactly the electromagnetic component comes in. And it is the same interaction, it is the same media, and you can see, depending on the position of the particle, okay, I mean, you can have shower energies deposited a totally different way. So this varieties, okay, I mean, which happens, okay, I mean, is really makes, okay, I mean, the energy measurement in a hadron calorimeter quite complex. I'll come to the energy measurement in the things. In a hadron shower, the scale is the collision length, which is related to the inversely related to the cross section of the process, and the shower maximum happens at a place, okay, which is logarithmically increasing in energy. So here again, okay, there is a logarithm. The size of the detector depends on the logarithm of the maximum energy which you want to have. And the decay of the shower is slower. It follows a power law, and the transverse dimension is controlled by the lambda. So it is almost constant. Okay, I mean, it does not depend on the energy of the particle. Okay, it's essentially run by lambda, and obviously lambda is much larger than the molar radius. Okay, so the size of the hadron shower is much larger than the size of the electromagnetic shower. Now, so this is how the showers are formed. Then you have to get this shower energy, to convert into some sort of a measurable signal, and you eventually convert that into some sort of electrical signal to record in the detector. So there are essentially three processes by which you can do this conversion. One is this ionization process. I think David gave an example of the liquid argon calorimeter in Atlas, where the energies which is converted in the liquid argon calorimeter will come in this is ionizes the electrons and ions, and they're drifted by the electric field, amplified and collected in the electrical pulse. Okay, this is a very standard way of measuring the calorimetric energy. Then also you can use excitation process. This is examples of the scintillation light emission in the organic or inorganic materials. The thing is, whenever the light is produced, it has to be a transparent medium. So the light has to be transmitted to the photodetectors and converted into photoelectrons, which is again amplified and collected as an electrical pulse. And some of the materials are not, doesn't have the scintillation light, but there will be a Cherenkov radiation. And this Cherenkov radiation always traverses or come in with this, the Cherenkov radiation happens when the charged particles in this shower traverses with a speed higher than the speed of light in the medium. And they will emit radiation and they will be converted into a signal, as in the case of a scintillation light. The example is a late glass calorimeter. But one has to remember that all Cherenkov radiation is present in all materials. So it is not just present in late glass calorimeter, it's also present in places where you have got plastic scintillators or even late tungsten crystal. There's a strong component is there which comes from the Cherenkov radiation. So one cannot ignore Cherenkov radiation in getting the signals from the calorimeter. Now, the next thing is the how you can try to get the signals. Now, there are two things you have to remember. One is the generation of the signal, other is the collection of the signals. Now, if the generation of the signals and the collection of the signals happens in the same medium, these are called homogeneous calorimeters. So for example, there are the crystal calorimeters, which is used in CMS, for example. What happens is the late time state, that fully absorbs the electrons and photons, and the scintillation or Cherenkov light, which is produced in the late time state, is collected, and that is converted into electrical signals, and that is a completion of calorimetry. That is the homogeneous calorimeters. But you cannot afford to have homogeneous hadron calorimeters. That will be too expensive, and that's why there you separate out the role of the absorber and the process which really collects the signal separately, and then you lose a part of the energies which is generated in the absorber itself, and you sample a part of the things, a part of the energies which is there, and then when you try to calculate the total energy of the things, you have to really take care of the energies which is lost in the absorber itself. So this is a thing which is called a sampling calorimeter, and since you lose a part of the energies which is there, obviously there will be sampling fluctuation which comes in the energy resolution. Now, the only as I said, you cannot afford to have a hadron calorimeter which is fully homogeneous. I at least have not come across a fully homogeneous hadron calorimeter, but there have been some studies on paper, okay, for fully homogeneous hadron calorimeter, but that I think, okay, can be done only on piece of paper, not on real practice. Only electromagnetic calorimeter can afford to be homogeneous type. They utilize either scintillation or Cherenkov radiation in the medium. Now, when one has to choose what type of medium one has to have, one has to see, okay, the various different aspects. One has to see the size of the detector. The size of the detector is determined by what is the, if you want to absorb the total energy, okay, I mean, so total energy means, okay, I mean, you roughly have 25 radiation length or something over 20 radiation length of the material. So if the radiation length is small, only then you can afford, okay, to have a compact calorimeter. Then you have to worry about how fast the calorimeter will work. So sometimes, okay, the calorimeter response is you get an enormous amount of light, but it takes quite long time, okay, for it to decay. Okay, so obviously you cannot afford to have that. Okay, I mean, in an environment where you have a 40 megahertz rate of particle production. Then, of course, you have to worry about the amount of light which is produced, and you have to also worry about other things, okay, like how easy to handle those things. So here is a list of various things. I think that sodium iodide is one of the oldest material, okay, which has been used, okay, in scintillating detectors. But the things, okay, we have come down to things like lead tungsten in CMS, mainly because of its two properties. One property is this, it is fast, and the other property is it has got a very short radiation length. Obviously, okay, I mean, the light output is not very good. Okay, light output is rather poor. So you have to worry about how to amplify the light output for that. In fact, okay, I mean, when we started talking about CMS electromagnetic calorimeter, we are not really concentrating on lead tungsten. We are concentrating on a thing called cerium fluoride. But cerium fluoride, the timing was good. Light output was better than lead tungsten, but it has got a larger radiation length. So one has to make it a much longer calorimeter. That was one consideration, but the other consideration was the cost. Okay, that's why you come in. We went to the lead tungsten for the thing. Now, what are the things we have to consider, okay, for making calorimeter? Obviously, okay, the cascading and shower creations are quite fast, but the timing of the signal generation process, which is the scintillation process, that has got its own timing, and so you have to really see, okay, the scintillation timing process, okay, and it's maybe worth considering the technique to be used, okay, to reduce the timing of the thing. The second thing is that, okay, I mean, whenever you are working an experiment, okay, I mean, apart from the particles which you like to measure, the other thing, there are lots of other particles which are produced. So I think there are a lot of radiation which is there. So the radiation environment is extremely important. So I think, okay, you have to find out something which is radiation hard. That means, okay, I mean, with the both for electrons, photons, that means the dosage, and for the neutron fluence, okay, I mean, it can handle pretty well. The total volume of the detector is a concern, because if you have a smaller volume, obviously the detectors which follow this particular detector will be smaller, so the cost of the detector will be less. Ease of usage, okay, you cannot afford to use hygroscopic material, so some materials did not have to take special care to control the humidity or temperature, and finally the cost. All these are the considerations for a calorimeter. So now most of the energy which is deposited in the calorimeter comes from very soft shower particles. Now in electromagnetic showers, the end of the shower is dominated by Compton scattering and photoelectric effect and not pair production and bremsstrahlung. So the angular distribution of shower particles is not so strongly forward peak. So geometries with fiber structure is as good as sandwich geometries. So I think, okay, I mean, that's why, okay, I mean, a Shashlik type of detector or a fiber detectors are as good, okay, I mean, for electromagnetic calorimetry. Now, sampling thickness depends on the type of the calorimeter. A typical shower particle in electromagnetic shower is about a MeV electron, which has range which is smaller than a millimeter in typical absorber material. Typical shower particles and hadron showers are 50 to 100 MeV protons and 3 MeV neutrons with a range of about 1 centimeter. Okay, so these are the things which have to be kept in mind. Okay, and if you really see, okay, the energy deposit in a calorimeter, okay, I mean, the Compton process gives a continuous energy range, and finally, okay, have got the pair production process, okay, in a late base detector. One of the things which you have to worry. Okay. Okay. One of the things which you have to worry, okay, we have to have when you measure the charge or signal, from the signal you can directly measure the energy. Okay, so if it is a proportional, that means, okay, I mean, it is very easy. You need a linear relationship for doing that. Now, in electromagnetic calorimeter, this linearity is maybe broken by two processes. One process is a quenching process, which is usually given by the Bach's law in scintillators, or it is a ionization chamber. It is also the quenching in the thing, okay, which gives rise to this, and also it gives rise to the saturation effect of the readout. If the dynamic range of the readout is limited, okay, obviously the linearity is broken. So I think, okay, this is one of the things, okay, where you have to really worry about the linearity in electromagnetic calorimeter. In hadron calorimeter, the things is much more complex. Okay, as I said, okay, I mean, hadron shower has got two components. One is the components due to the electromagnetic part comes from the pi zero production, and the other thing is for the ionization loss due to the hadrons. Okay, so the shower response due to electrons and hadrons is not one. Okay, it is different from one in most of the cases. And then on top of that, you have got this loss due to the binding energy. So E over pi is a very important factor, okay, I mean, for determining the thing. So you can have, you can try to compensate the thing by adding material, okay, which will give rise to, I mean, from the neutrons which is produced in the shower, it can give rise to fission, for example, and it produces new particles. So, for example, this WA78 experiment, which has got alternate uranium iron absorbers and plastic scintillators, it has got E over H, which is smaller than 1. Then the WA1, which I talked about, is nothing but iron and plastic scintillator. It has got a E over H, which is much larger than 1. And Helios is a uranium and plastic scintillator detector. It tries to manage, okay, E over H, okay, when very close to 1. So if you have E over H very close to 1, obviously you can get a better linearity with energy. Now, this is our CMS detector, which was exposed to the hadron beams, okay, in the test beam in 2006. And what one sees is that, okay, I mean, you have the incident energies, which is well known, okay, from the beam energy, and you can clearly see the energy which is measured in the calorimeter for different types of particles except electrons. Electrons is pretty flat, but for all the other particles, okay, I mean, you have got a total nonlinear thing. So this nonlinearity is some big problem, okay, for any calorimeter, and we have to say, okay, how the nonlinearity can be broken. Now, if you have a pure calorimeter, homogeneous calorimeter, obviously you cannot take care of this nonlinearity. So here is sodium iodide, and if you hit a pion and you have an electron, obviously you cannot use the sodium iodide, okay, I mean, to take care of that. Before I talk about the compensation, I just say, okay, I mean, have a word about energy resolution. Energy resolution has got essentially three components. One component I have already talked, the fluctuation that are used by Poisson statistics, which is this 1/√E dependence. This is the shower fluctuation, as well as the fluctuation, quantum fluctuations in the photostatistics and the sampling fluctuation. These are the three things which contribute to the 1/√E. Then you have the shower leakage, which gives rise to a constant term. And also the calibration effect also gives rise to a constant term. And the electronic noise gives you 1/E. And since it is 1/E, okay, you can simply ignore that thing, okay, at very high energies. It is an important thing at low energies, but at high energies, okay, I mean, you can simply ignore that term. Now, this is one of the best sampling calorimeter, which is a lead liquid argon calorimeter. But if you look at the linearity of this calorimeter, you can see, okay, I mean, it is deviating from linearity, and this is the energy resolution also, okay, I mean, is affected, okay, by essentially by the sampling fluctuation more, okay. The shower fluctuation is there, okay, but the sampling fluctuation is the one which has killed the intrinsic resolution of the calorimeter. But it is surely is a very, very good calorimeter. It's got, apart from the energy resolution, it has got position resolution, and it has got a directional resolution, which has helped them, okay, to find the direction of the photons in the Higgs to gamma decay. Okay. Now, the nonlinearity in the response, as well as the anhydronic showers, are due to this E/H ratio. This is overcome by a technique in the by having converting the neutrons by use of hydrogen enriched material, but this cannot give any resolution better than 10% in 100 GeV. This is a table, okay, of various different E/H, okay, which has been measured, okay, and you can clearly see, okay, I mean, none of them is very close to 1. They're very large. The alternate to that, you have the so-called particle flow method, which is a combination of a precision tracker and a precision electrometric calorimeter and ordinary hadron calorimeter. The charged particles are measured with the tracker, photons and electrons are measured with the electrometric calorimeter, and after that, okay, there is only 10% of the energies which is left, which is measured in the hadron calorimeter. So if you have a pure calorimetric measurement, the energy resolution will go like this. And if you can use this particle flow method, obviously the energy resolution improve enormously, particularly at low energy. Okay, it goes from 45% to 15% at energies around 20 GeV. So this is a method which has been used, okay, by almost all new detectors. The last thing which I talk about is this dual readout scheme. As I said, okay, I mean, all particles, all detectors which are scintillators have a component which is Cherenkov radiation. Now, Cherenkov radiation is pretty fast, and scintillation is slower than Cherenkov radiation. So if you somehow can distinguish the Cherenkov part and the scintillation light through the timing of the detector, okay, I mean, you have got the Cherenkov component is purely electromagnetic, whereas the scintillation component is a mixture of the two. Okay, I mean, it has got a hadronic as well as electromagnetic component. So I think, okay, this particular dual readout scheme was invented by Richard Wigmans, and he made a prototype detector called DREAM. And where he measured the total charge and the quartz fiber and the scintillation fibers. And the quartz fiber and the scintillation fibers, quartz fibers measure this scintillation, Cherenkov, and the scintillation fiber measures the both. And if you combine the two, you can see, okay, the energy resolution has gone down from 14% to 5%. So I think people have really talked about many things, okay, of doing that. So why not try to combine, okay, I mean, the dual readout as well as the goodness of a crystal calorimeter. So in future, okay, I mean, when they thought about this idea detector for FCCE, they have a calorimeter, a dual readout calorimeter surrounding a crystal calorimeter. And obviously with that, okay, I mean, they get a precisions for example, the mass resolutions of WZ and things, okay, at the level of 3%, which is excellent. Okay, so I'll stop here.
Question?
I have two questions. The first one is on slide 8, where you showed the electron and positron energy deposition. So they, why does it differ for electron positrons at low energies?
Which one? Yeah.
So that on the top, electron positrons are deviating at low energies. The DDX.
This I'm not sure, but they are different, okay, at low energies, yes.
Okay.
The ionization loss.
The ionization loss is different for electron positrons at low energies because of that. Okay. And another question is in slide 12, where you said that the fraction to the EM energy increases up to 50%. Why is that for the hadron showers?
This is, okay, I mean, the amount of pions which is produced, okay, I mean, that really increases as a function of energy, okay, so that's fine.
Okay, but overall it's 1/3 of the pi zeros that are depositing energy in the, okay, but the overall number of pions has increased. Okay, thank you.
One third in each interaction. Yeah. So the energy increases, the interaction is more and more. So if we stay with one third goes to the pipe.
Thank you very much, Professor, for your insightful presentation. My question also related to slide number 8. Slide 8. Okay. In the plot that you mentioned quantum photoelectric effect and pure production, right? And why not there is a triplet production phenomena? Triplet production. As you know,
I don't remember. I mean, it's the cross section of the triplet production is smaller than that. Okay, so
That's certainly higher.
huh?
That's certainly higher.
Yeah, it's higher. I mean, it's much smaller than that. Yeah.
that means triple production.
It's much smaller than these are the 3 dominant cross sections.
Yeah, okay. That is the reason. Okay, thank you, sir.
Okay, I think I will stop the discussion here because we are little late. So further discussion may be in the tea table.